In this short lecture, I'd like to summarize the key properties of rational preferences. So let's first remind ourselves how we're representing the preferences of a decision maker. Suppose X is the set of outcomes or the objects of choice or what have you. A decision maker's preference over X is going to be represented by, there are three relations that represent the decision maker's preferences. First of all, there's the relation of strict preference, where A is P related to B, means that the decision maker strictly prefers A to B. The second key relation that represents a decision maker's preference is the indifference relation. So this is going to be a relation on X called I, where we write A, I, B, which means that the decision maker is indifferent between both A and B. And finally, there's the non-comparability relation. So let's call this the relation N. We write A, N, B to mean that the decision maker cannot compare A and B. So A and B are incommensurable or non-comparable for the decision maker. Now, the minimal constraints, just some basic constraints that we would place on these three relations, just so that they match our intuitions about how these relations should work, should be, first of all, for all X and Y, exactly one of these four properties must hold. Either X must be strictly preferred to Y must be strictly preferred to X, the decision maker must be indifferent between X and Y, or the decision maker can't compare X and Y. So intuitively, if P, I, and N represent the preferences of a decision maker, then one of those four properties must hold. 2, P must be an asymmetric relation. So what does that mean? That means if X is strictly preferred to Y, so X is strictly preferred to Y, then it cannot be the case that Y is strictly preferred to X. That's what it means to be asymmetric. If X is related to Y, then Y is not related to X. And intuitively, this makes sense. If I strictly preferred X to Y, then it can't be the case that I would strictly prefer Y to X, because I wouldn't have an incentive to trade X for Y. Third, I should be reflexive and symmetric. You can really read that off of how we stated the definition. So if X is indifferent with Y, well, that's just a property of X and Y. So of course, Y must be indifferent with X. So unlike strict preference, your indifference relation needs to be symmetric. And clearly, everything should be indifferent with itself. You should be indifferent between having a glass of wine and having a glass of wine. And then finally, your non-comparability relation should also be symmetric. Again, that's sort of built in to how we even stated the definition. If X is non-comparable with Y, then of course Y is non-comparable with X. It wouldn't make sense to have Y be able to be compared with X, but X not compared with Y. I don't really understand how one would have a relation like that and call it non-comparability. So these are just basic mathematical constraints that we would place on these three relations, just to think of them as minimally representing what a decision maker's preferences are. But of course, we're not just interested in the minimal constraints. We want stronger constraints. We want preferences that are meant to represent rational preferences. So a pair P and I is a rational preference relation. So notice I'm not including the relation N, and I'll explain why in just a second. So a pair P and I, so your strict preference relation and your indifference relation, is called a rational preference on X, provided that P is a relation on X, I is a relation on X, and P satisfies asymmetry and the important property of transitivity. That means that if X is strictly preferred to Y and Y is strictly preferred to Z, so if X is strictly preferred to Y and Y is strictly preferred to Z, then it has to be the case that X is strictly preferred to Z. That's the definition of transitivity. And this has to be true for any elements of X. So your relation P representing your strict preference is what's known as a strict weak order. So any relation that satisfies asymmetry and transitivity is called a strict weak order. Your relation I must be what's called an equivalence relation. That is, it has to be reflexive, symmetric, and transitive. So not only is your strict preference transitive, but also your indifference is also assumed to be transitive. Now, you might be wondering, why don't I include N, the non-comparability relation, in the rational preferences? Well, that's because we assumed the second key property, which is completeness. So the two key properties are transitivity and completeness. Completeness says, for any elements x and y, exactly one of these three properties hold. Either you strictly prefer x to y, you strictly prefer y to x, or you're indifferent between x and y. So exactly one of those three properties must hold. This means in particular that a rational preference can't have any non-comparable elements. So you can't have any elements that are not comparable. So the N relation must be empty. There must be nothing in the N relation. So note, this means that if we're talking about a rational preference for a decision maker, then you only need to specify what your strict preferences are, because your indifference relation can simply be inferred assuming completeness. In particular, if you don't strictly prefer x to y and you do not strictly prefer y to x, then the decision maker must be indifferent between x and y. So in a picture, this means that if we know that the decision maker strictly prefers, say, x to z, and strictly prefers, say, y to z, but there's no strict preference one way or the other between x and y, then by completeness, it means we're not in this case, we're not in this case, so we must be in that case. So that x and y must be in, the pair xy and yx and xx and yy. That must be in the indifference relation. So for that reason, typically when you specify a rational preference on a set X, you only ever write down or describe what the agent's strict preferences are, because you can infer what their indifferences are. So let me conclude by just writing down all the possible strict preferences on a set with three elements. So suppose you have three objects of choice, A, B, and C. So A might represent a glass of red wine, B might represent a glass of white wine, and C might represent lemonade or what have you. It turns out that there are 13 possible rational preferences on X, and they fit into just a few categories. So first of all, the decision maker might have no strict preferences. You might have there's zero strict preferences. That just means your strict preference relation is empty. There's no strict preference. What would that mean? That would mean that you're indifferent between A, B, and C. So I would draw the preference this way. I would say that the agent is indifferent between A, B, and C. They're all at the same level. So that's one possible rational preference on X. The second possible rational preference, so these three all fall into the same category, this would mean the decision maker is indifferent between two elements, and both of those elements are strictly preferred to the third element. So these three different strict preferences are three ways that could happen. So you could have A and B is strictly preferred to C. You could have A and C is strictly preferred to B. Or you could have B and C is strictly preferred to A. So this strict preference is represented there, this one is there, and this one is depicted there. Okay, so these all fall into the category where you have two things that are tied. You're indifferent between two things. Those come in first place, and then in second place is the other object. A second or a third category is that a decision maker is indifferent between two elements, but the third element is strictly preferred to both of those. So these three strict preferences represent those situations. You could have B and C are tied for second place, and A is uniquely in first. You could have A and C are tied for second place, and B is uniquely in first. And finally, you could have C uniquely in first, and A and B are tied for second place. So this third strict preference is represented there. The second one is represented by that second box, and here is the first one. And then finally, there are 6 ways you can arrange the strict preferences in a linear order. So you could have the decision maker prefers A over B over C. The decision maker could prefer B over A over C. The decision maker could prefer, well, let me do this a bit more systematically. So we could have A over C over B. You could have B over A over C. You could have B over C over A. And then finally C over A over B, and finally C over B over A. So those are the 6 ways in which a decision maker might have a linear preference. So have something in first place, something in second place, something in third place. So these are the 13 possible rational preferences on the set X. You can arrange the things in a linear order, and there are 6 possible ways to do that if there are 3 elements. There are 3 possible ways in which there's a unique element in first place and 2 things tied for second place. There are 3 possible ways in which 2 things are tied for first place and the third thing is in second place. And then there's 1 way in which the decision maker is indifferent between all the elements. Those are the 13 possible ways of having a rational preference on a set X.